Hi, my name is Daniel Lejeune, and in this video, I'm going to talk to you about the multi-arm bandit problem on a graph. In particular, I will talk about how we can find the set of arms in a multi-arm bandit that are above a specific threshold, given that we have information about the correlation of the rewards of the arms in the form of a graph. First, let's introduce the thresholding bandits problem. We are given access to a set of arms representing distributions having varying means, which we can sample from as we like. One question we might want to answer then is which of these arms have means above a certain threshold? And then, since we can only observe the arms through random samples, if we can choose a strategy for sampling the arms, what strategy will get us to the correct answer to this question the fastest? This thresholding bandits problem has been addressed by a few groups in recent years. In this work, we modify the problem setup to introduce a new information source. If we have information about how the means of the arms are expected to be correlated with one another in the form of a graph, then how much easier does this problem become to solve? Let's be a bit more formal. We have n arms, nx by I, each having mean mu I and an R sub Gaussian distribution. We want to identify the superlevel set of which of the arms have a mean greater than a threshold tau. But we will only concern ourselves with evaluating the accuracy of our estimate of this set for the arms that are at least epsilon away from the threshold. We are allowed to select arms for t rounds with the strategy pi t, which can be adaptive, and we will draw samples from the distributions according to our strategy. Lastly, we have a graph which captures the similarities between the arm means, and from its vertices, edges, and edge weights, we can obtain the graph Laplacian L. Our algorithm for solving this problem is called GrAPL, the graph-based anytime parameter light thresholding algorithm. It combines the adaptive strategy of the anytime parameter-free thresholding algorithm, APT, with regularization of the estimator using the graph Laplacian. GrAPL consists of three main steps. First, we form an estimate of the distance from the threshold for each arm. Here we see the parameter epsilon from before, which serves as a buffer to keep these terms away from zero. Next, we compute confidence proxies, which serve the same role as the upper confidence bound in UCB-type algorithms. The higher one of these values is, the less likely we are to gain any more useful information about that arm if we draw another sample from it. Here, n is the number of times we have sampled the arm previously, and alpha is a small value that keeps the confidence proxies from being equal to 0 when we haven't drawn any samples from a particular arm. Lastly, we select the arm with the smallest confidence proxy as the next arm to sample. Now let's talk a little bit more about the estimation of the means. We estimate the means by solving a mixed objective of the squared error of the observed samples for each arm and gamma times a Laplacian-based penalty term, which penalizes the squared distance between values for adjacent nodes in the graph, as well as the two norm of the values to help with stability. It is this regularization that will allow us to leverage information sharing between the arms, so that we can converge to the solution much faster than other adaptive strategies. To demonstrate GrAPL, let's consider a simple line graph, where each node has a mean value, which I've indicated by both the color of the node as well as the node's y-position in this plot. The dotted line represents the threshold. Let's make a new empty estimate of the means for GrAPL. We will start with sampling a random node, observing a value, and updating our estimate. Then we will begin sampling nodes according to our strategy, updating our estimate as we go. Before long, we will approach the true solution, which may happen, as in this example, even if we take fewer samples than the number of nodes in the graph. We can quantify the performance of GrAPL with a theoretical guarantee. If the number of rounds is larger than a scalar multiple of the Laplacian smoothness measure of the true means, a condition that is easy to satisfy when adjacent nodes in the graph have similar means, then we have the following form of a bound for the error of the algorithm. This quantity dt is what we call the effective dimension of the graph, and very often for graphs of interest this quantity is very small, much smaller than the number of arms. We can see from this expression then that once the number of rounds is on the order of the effective dimension, then the error converges exponentially to 0. Thus, the number of rounds we must play to achieve a good solution depends on the smoothness of the means on the graph and the effective dimension of the graph, rather than the number of arms, which allows the algorithm to outperform other thresholding bandit algorithms like APT. Let's consider an example to demonstrate the advantages of GrAPL. Here we have a graph generated by a stochastic block model with 500 nodes divided into two clusters. We will use the cluster labels as the arm means. We'll run GrAPL in this corner. In this corner, we'll run an algorithm that uses the Laplacian regularized estimator like GrAPL, but selects arms at random every iteration instead of selecting adaptively. And in this corner, we'll run APT, which has the same adaptive strategy as GrAPL, but doesn't use the graph information. Let's plot the error after each step for 500 steps. APT, unfortunately, must sample each arm at least once first, so in 500 steps we can't realize the benefits of the adaptiveness. The random sampling strategy, on the other hand, is not robust to the noise of the samples it receives early on. However, the adaptiveness of GrAPL makes it robust to noise, and it is able to converge to the solution within 500 steps. If you want to know more about this work, I encourage you to check out our paper, where we include more such as lower bounds on error for certain graphs, discussion on optimality and tuning, and experimental results. I would like to thank the agencies that sponsored this work, and most of all, thank you for listening.